I'm sure you all recognize that noise, and I'm sure you all have some deep rooted emotional response to it. It might be anger. I wish I was still asleep. Why is my pager going off? Maybe it's happiness, because now you know it's your time to be a hero. Whatever emotion it invokes, I'm sure you've all been there when you receive a page, you go and try and diagnose the issue, and you have absolutely no idea what has caused the thing to go wrong. And before you know it, you're command effing your way through a giant wall of text log files. These things got even more challenging as you all started building distributed systems. Now, instead of looking at a log file on a single machine, you're looking across lots and lots of machines that are all communicating with each other. And then you made the excellent decision to make your system event driven. You looked online, attended conferences like this one, and you realized that event driven systems are the only way to build resilient, scalable systems, right? And now you're sat there at 3 o'clock in the morning wishing that you hadn't, because you can't work out what caused your system to go wrong. And that's what you're going to learn about in this talk. You're going to learn some patterns and practices for adding observability to systems that are built prioritizing asynchronous communication. And you're going to walk away from here with some practical things that you can implement in your systems to help that experience at 3 o'clock in the morning be just that little bit easier. I'm James Eastham. I'm a serverless developer advocate at Datadog, but this isn't going to be a talk about a specific SaaS product, a specific technology or provider. This is simply a talk about observability in asynchronous systems. Now, if any of you have heard me talk before, you'll know there's one thing I love talking about almost as much as event-driven systems, and that is, of course, pizza. For the rest of this talk, I want you all to imagine that you're a developer working for a completely fictional pizza delivery company, and your pager's just gone off. Maybe it's the middle of the afternoon, there's a big sporting event on, lots and lots of people are trying to order pizza, and they can't get the pizza that they want. So now it's up to you to work out what has gone wrong in the system. And to help you understand that, let's actually understand how the plant-based pizza application works. And to take a step back for a second, once upon a time, your pizza restaurant had an application that looks something like this. Simple application, single monolithic process, single database. Life was simpler then. But as you started to grow, and I mean, look at the state of these pizzas, of course you're going to grow, your system evolved into a distributed set of microservices, all communicating synchronously, HTTP APIs everywhere, everything talking to each other through this set of well-defined APIs. This started to give you a lot of pain though. Pain because of how tightly coupled your system was. Of course, coupling isn't necessarily a bad thing. If you built a truly decoupled system, it would honestly be pretty difficult to get any meaningful work done. Event-driven systems aren't decoupled. Decoupling points towards there being no interaction at all. Instead, event-driven systems are loosely coupled, and loose coupling is a good thing. It was even captured in a common saying related to software architecture that you should aim for low coupling and high cohesion. Now, cohesion you've already solved pretty well. The idea of cohesion is that things that change together should live together. And you've already got that with your microservices. So you decide to start making your coupling as loose as possible. You've taken that synchronous system communicating with APIs and got you to where you are today. Your system uses almost entirely an event-driven architecture. It's using messaging to communicate, and at a very high level, you've got 5 different microservices. All this inter-service communication uses events. And to give you an idea how this flows at a functional level, a user may come along and try and place an order for a pizza. They're going to hit the order processing service with a create order request. That might come from the web app, that might come from a mobile app. The order service is going to process that request and raise an order confirmed event. The kitchen service is interested in that order confirmed event, and that's going to kick off an internal business process where someone's actually going to go off and create your pizza. Once the pizza is prepared, that's then going to raise an order prepared event, which the delivery service is interested in to then go and get somebody to deliver your pizza to you. Of course, the order service is also listening to that order prepared event so that when you come along furiously refreshing your mobile app to try and work out where your pizza is, the state of the pizza is kept up to date. Sounds fun, right? And you're already building an event-driven system. So I'm assuming that you already know what an event-driven architecture is. So now you're in this position where you need to observe it. You need to work out exactly what is happening. What do we actually mean by observability? The word gets bandied around a lot nowadays. It's become a bit of a loaded term. And almost every conversation about observability comes back to the three pillars of observability. Those three pillars being logs, metrics, and traces. Now, of course, these are really important areas to think about. But I think this misses the bigger picture. These things are how you might implement observability, but why do you actually need observability in the first place? It's always important to ask yourself why. An observable system should give you the ability to ask questions of your system you didn't know you needed to ask from a position that's outside of your system. Asking questions you didn't know you needed to ask. That's quite an odd way of putting it, right? Let's try and understand exactly what that means. And when you think about the components of your system, imagine you had an outage a few weeks ago. Maybe your database went offline inside your order processing service. And maybe that went offline because of an increase in disk space. There was no disk space left inside your database. So you went along, you added additional disk space, everything was happy. Once you've done that, you're probably going to have put some kind of monitor in place to make sure that doesn't happen again. Maybe you put a monitor in place to check when the disk gets more than 70 or 80% full. That way you can go along and preemptively add additional disk space if needed. Because you put them things in place, the chances of your system failing in that same way again are massively lower because you're now checking for it. Yet in distributed systems, you're dealing with unknown unknowns. Distributed systems fail in new and novel and different ways all the time. Distributed systems are being updated frequently by different teams of people with different priorities, different release cycles, different SLAs. Modern systems are constantly evolving to meet changing business requirements. So how exactly can you possibly put these monitors in place to know how your systems are going to fail? These things get even more difficult when you start building event-driven systems. Not only are you now dealing with systems that are constantly changing, they're also communicating completely asynchronously. This is a form of complexity. And there's two different types of complexity you'll see in systems. There's essential complexity. Essential complexity is the complexity inherent to the problem you're trying to solve. Accidental complexity, though, that's complexity that comes from the decisions you choose to make. Monoliths, microservices, event-driven systems, Kubernetes, serverless, all these things have their own type of complexity. Some things are simpler. In some ways, some things are more complex. If you think back to the historical version of your pizza restaurant, it is much more easy to reason about. You've got a single running process, a single database, one line of communication. If things go wrong, you've got a pretty good idea where you need to look. But now you're in this position where you've got all these event-driven microservices. Some things have got simpler. Some things have got a lot more complicated. You've got quite a few more moving parts to monitor, and reasoning about your system is difficult because cause and effect becomes incredibly difficult. Understanding the upstream systems that affect your system and the downstream systems you have an effect on is one of the most challenging parts of building an event-driven system. But what is it that makes it so difficult to understand cause and effect? Imagine back to when you were prioritizing synchronous communication, good old-fashioned HTTP API calls. Here, cause and effect is reasonably easy to establish. The order service makes a call to the kitchen service. You can almost follow the bytes across the network. And then you're going to get some kind of response. That might be a timeout. That might be a slow response. It might be a happy response, but you're going to get something. It's reasonably straightforward to understand that the order service had an effect on the kitchen service because it's calling it directly. Compare that to your event-driven system. Here, none of your services in your system have any kind of direct communication with each other. Services simply publish events and then they go on and get on with their day. They don't care who uses the events. And equally, as a consumer, You just consume events and work with them and hope that the systems upstream from you are nice enough to never change. This challenge with cause and effect makes distributed tracing the most important part of an event-driven system. Being able to understand how a request flows through your system is absolutely vital. And to settle on some terminology at the very top level here, you have a trace. A trace is the overarching end-to-end flow of a request. And then a trace may be made up of lots and lots of different spans. And these spans could cover multiple different backend systems. Spans can also have tags. Tags allow you to add contextual information, and it's this that starts to allow you to ask the questions of your system you didn't know you needed to ask. Let's actually see this in action with one of the perceived benefits of building an event-driven system, and that is evolvability. Event-driven systems are great for changing your system over time, right? But it's precisely this feeling of pseudo evolvability, this ability to change your system in any way at any time, that gives you one of the best examples of the importance of observability. Think about this the order confirmed event that gets published. The order service publishes the event, the kitchen service consumes it, but the event doesn't actually contain any information about what the kitchen needs to go and prepare. So the kitchen service may need to make a call back to the order service to actually get the details of the order. This on its own might seem okay, but remember, your system's evolvable. So maybe a whole bunch of other systems start popping up and they also start consuming that order confirmed event and they also start making callbacks. And before you know it, your entire system is on fire. One of the core principles of EDA is that services are unaware of the downstream consumers of their events. And whilst this is technically true, you need to be really, really careful with this statement because although you don't care who's using the events, you should really be a little bit interested in what they might do once they receive that event. Distributed tracing can be really beneficial here. Having a system that is observable allows you to understand these challenges. You can now start to correlate when a create order request comes into your order service and you go off and publish the event. You can see the downstream system consuming this event, and the different colors on this image denote different services. You can see that the order created event was received, and then the get request came back to your service. You can now see the effect of you publishing that order created event is that another request comes back to your system. This allows you to start to ask questions of your system to understand cause and effect. And you can make informed decisions once you have this information. Maybe you decide to change the structure of the event. You add all the additional information to the event so that downstream systems don't need to make that callback. Simple, you think. And as you expect, you roll out this new version of the event, these additional properties get added, and suddenly downstream systems no longer need to make that callback. Problem solved. You've used your observability data to make a change to your system. Fantastic. And now you're full of confidence. You've made a change to the structure of your events, you're evolvable and observable. And now you have another change to make. You need to make your application support multiple currencies. You've changed your event schema once, surely you can just go off and change it again, right? And that's what you do. You add the currency as part of the value field. So instead of publishing the value as a decimal, you're now publishing it as an object with the value and the currency. And the kitchen service might be completely okay with this. And you know the kitchen service is using this event because you can see that in your tracing. But what you didn't realize is that an analytics service has also been created now. Remember, your system's evolvable. Services can pop up at any time. And the analytics service really, really care about that currency field. And now you've just broken a system that you didn't know existed. Now what? Observability is your friend again here. The schema you use to structure your events is a really powerful thing you can use to help add observability to your systems. Adopt some kind of defined specification for your events. The cloud event specification is one such spec. And there's some really useful fields in here. The first being the data field. The data is the actual contents of the event, the actual payload. You've then got the data content type. This tells a consumer what type of data is going to be in the data property. The time tells the consumer when this event was published, and the ID is a uniquely generated identifier generated at the point of publish. And then in this conversation around evolvability, you've got the source and the type at the top. The source tells the consumer where this event came from, and the type tells the consumer what type of event this is. Notice it's suffixed with a version number. That is incredibly important. You've also got this trace parent property. This is also part of the cloud event specification. This is a way to pass distributed tracing information as part of the event you publish. Now, this trace parent you can see here is a W3C trace context. You could also just pass a correlation ID, some common identifier that goes from system to system to system. But if you're adopting a specification for your events, it kind of makes sense to adopt another standard as well. And this long, complicated string is actually reasonably easy to understand. It's broken down into 4 parts. The first is the version of the trace context. It's zero-based versioning, so there's only one version at the minute. You've then got the trace ID, the ID of the overarching trace, as well as the span, the specific span that this event was published from. And finally, you've got some flags at the end. This allows you to pass sampling information in your tracing down to the downstream consumers. Now, when you publish an event from your system, you can propagate that trace context and continue that trace through the downstream system. And remember, context is really important. OpenTelemetry defines a set of conventions that message-driven systems should follow. This defines a set of tags that all spans related to messaging should have. Things like the operation name. Are you sending or are you receiving? The message system being used, in this case, AWS SQS, and even the name of the destination, in this case, the queue. Personally, I also find it really useful to include the version and the type in here as well. This is what will allow you to evolve your system in a more observable way. Today, you're publishing version 1 of your already confirmed event, and maybe you start publishing version 2 with that new currency field. And for a period of time, you're going to publish version 1 and version 2 of your event. And because you're propagating this trace context, you can go to your observability backend and ask the question, who is using version 1 of the already confirmed event? Because you've got that context on your traces. This will allow you over time to go and speak to individual teams and get everybody to migrate over to version 2 of your event. The way you document your event-driven architectures is also a vital component of your observability strategy. Who here is familiar with the idea of API-first design? If you are, the idea of API-first design is that when you build your system, the first thing you define is its API. Your front-end team and your back-end team may have a conversation, agree on the format of the API, and then when it comes to integrating later, everything is lined up and ready to go. So when you're building an event-driven system, you want to practice event-first design. The events you publish are the API of your system. And I want to give a really quick shout out to Event Catalog. Event Catalog is an open source project built by David Boyne, and it makes it really easy to document and discover event-driven systems. Now, at the moment, Event Catalog requires you to upload documentation files, but on the roadmap, there's going to be plugins for various different event brokers to allow you to build a self-documenting event-driven system. That idea of a self-documenting system is kind of interesting, isn't it? You've got events flying around your system, you've got producers and you've got consumers, and one of the most valuable things you could see are the actual events that are flying around, because documentation gets out of date, people forget to update it. In this code snippet here, you're logging the actual event payload into your logs and also adding that as a tag to your spans. So in my observability system, you can see exactly what events are flying around. And if you go and do this, someone somewhere in your company, probably a security person, is going to have an absolute heart attack, because if you implement this, it would be pretty easy to expose sensitive information into your observability backend. So you want to see the events that are moving around, but equally you want to be careful about the data you store. A practice I'm a really big fan of is storing the schema of the event, not the event itself. Most programming languages will allow you to actually extract the schema of a JSON string, and now you can store that schema in your observability system. Having all this context allows you to play detective, to ask questions of your system. The more context you can add to your spans, the better you can play detective, to ask questions of your system. This is the power of tracing in distributed systems. This isn't a silver bullet, though. It's not as simple as you might think. Here's an example of a full end-to-end distributed trace from your pizza restaurant. You can see that this event spent 300 milliseconds inside Amazon EventBridge. It spent 117 milliseconds inside SQS before it was consumed by a downstream service. This is incredibly useful to be able to see the exact transports, the exact flow that an individual event went through. This is information that you will probably need to extract manually. For example, when you receive an event from SQS, SQS includes the timestamp this message was received by SQS. You can use that inside your application code to infer that time taken for a message to flow through a given message channel. And most message transporters, at least in AWS, will give you this information to be able to infer that time spent in flight. You can use that to then start a downstream span linked back up to that publishing one. Looking at this screenshot again, though, you can see that there's these really two long purple lines. And these two purple lines take a disproportionate amount of time relative to the rest of the trace. This is some kind of long-running business process. And business processes can take hours, days, even weeks sometimes. Trace propagation is incredibly useful, but it can also cause a lot of confusion. There's another scenario here. Imagine inside your pizza restaurant, every day you need to analyze all the orders that have been confirmed that day. You need to run a daily job. If you were a developer debugging the daily job, you wouldn't want to see your daily job split across all of them upstream traces. So what's the answer here? What's your options? The alternative you have to trace propagation is span linking. With span linking, instead of propagating the trace, you simply create a link. You link a span in one system to a span in another system. This keeps these processes independent while still allowing you to understand cause and effect. Which begs the question, which is the right one to choose? The best way to think about this is to think of a unit of work, or think of a business process. Maybe an order comes into your order service, the order confirmed event gets published, and the kitchen consumes that. That's probably pretty useful to understand as one thing. And then the kitchen service is going to start its own internal business process. Maybe that internal process for the kitchen service, you use a span link to link back to the upstream call that caused that workflow to start. You're probably going to need a balance of both. What this does give you once you have all this in place, though, is this ability to understand dependencies, to understand cause and effect. You can see that your product management system has an upstream dependency on a pricing service and a downstream dependency on various other services. Observability gives you the required nuance to this statement. Because although you don't need to care what your downstream services are doing, it certainly helps to understand who is relying on you and who you rely on. Having all this in place gives you the required things you need to be able to go and debug that issue and make sure that your users can get their pizzas. So what to take away? I realize this is a really high level look at observability in distributed systems. What you need to start thinking about is cause and effect. Think about how you can best understand exactly what caused your system to run. If you're building a new service or a new piece of functionality, ask yourself the question, how will I understand what has caused my system to do some work? And then think about this idea of asking questions of your system you didn't know you needed to ask. Making sure you add context to your request to allow you to spin and look at your data in different ways. And then finally, think about things both at a macro level on individual requests, but also at the bigger picture as well, the macro view, giving you a higher level look into your system at a bigger picture. A pull request template for a company I used to work for, I used to have the question in the template, when this code reaches production, how will I know that it's actually in production? How will I see it running inside my observability backend? If you can answer that question, you'll always be in a good place to debug your systems. Thank you all very much for listening.